Hello, good morning. My name is Jose Ruiz. I'm working for AdaCore. And today what I'm going to talk about is about the implementation that we have done for Ravenscar on multiprocessors. This is based on some ideas that we were sharing at the AdaCore office. We were having some ideas about how to do that, how to take advantage of the new hardware platforms that are going to be used in embedded systems, probably not today, but in the near future. So that with these ideas, we went to the last International Real-Time ADA workshop, where we were discussing these things and having interesting feedback. From that point, we said, well, it could be interesting to implement that. So we found an intern who is Fabien Chouteau, who was interested in working on this and who did a very good job at that and did all the implementation on top of Leon 3, which is a multiprocessor platform used in the space industry. And now Fabien is now a full-time employee at AdaCore. We liked what he did. So first, this is the outline of the presentation. We'll first talk a bit about the problem domain, what are we talking about. Then we'll talk briefly about what support is in ADA 2012 for multiprocessors, focusing mostly on the definition that was added about Ravenscar and multiprocessors. Then we'll talk a bit about the implementation that we did and some conclusions. So first, what's the starting point? So first is why? Why do we want to use this kind of complex architecture on real-time systems? Well, the answer is because you always need more speed. You need more processing power every day, and single core architectures are not enough for that. You need to keep increasing, and as in any other industry, they are looking at multiprocessors as the way to increase processing power. In addition to that, in the embedded market, there is also an issue with power consumption. Increasing clock frequency is going to consume a lot of power. If you want to increase processing power and keep your energy utilization low, you need to move to multiprocessor architecture. So that's why. And we see that multiprocessor are being used in many other domains. So let's try to use them. So now, the problems. Well, I don't need to talk a lot about problems because we have had just a presentation before myself talking about problems when you have parallelism. So first, you need to design your application. You are on a multiprocessor. You say if you want to take advantage of multiprocessors, you need to design your application so that you take advantage of that. It's not easy. You have all the problems with race conditions, deadlocks, and all that. So it's not evident how to do that. Then you need to integrate everything to implement. Not easy, because you test something in isolation, everything works fine. Put things together, doesn't work. Okay, so again, race conditions happening. And finally, when you want to validate, for example, your scalability analysis, there are very well-known techniques on monoprocessors that help you. When you move to the real parallel world, where you have real parallelisms, it's not that easy to do the scalability analysis. There is some work being done on that area, but it's not very simple to do. So this is major problems. as I said, in monoprocessor, for example, if you stick to the Ravenscar computational model, you have a very well known, very well established methodology for doing your analysis. You have rate monotonic analysis, response time analysis. You have tools for doing that. You have many people understanding what is behind, so no issue with that. Now, if you move to multiprocessors, there are many more variables in the design. The first thing is that there is global versus partitioned way of scheduling your system. You can decide, for example, I have this set of tasks. I want this set to run all time in this concrete processor. That's partitioned way. Or you say, I really don't care. I just want my operating system to do its best, trying to take advantage of my underlying hardware. So I'll leave my operating system do the work. If you have a look at the scheduling literature, you will see that sometimes you say, okay, I have a monoprocessor at this speed, I'll move to a dual processor, same speed, so I'll roughly get twice the processing power. Not true. Usually the concrete utilization that you can achieve is much lower than that. And then the algorithms, the scheduling algorithms are more complex. Preemption is different. You need to handle task migration. There is a lot of new things that you need to take into account. Simply the fact of accessing the memory, depending on the memory architecture, things that you can do safely on a monoprocessor are no longer safe on a multiprocessor. You need to use memory barriers. So it's a completely new world when you move to multiprocessors. So just to show you more graphically what we were talking about, this is probably the most important decision when you move to a multiprocessor architecture, is whether you want to go to the partitioned way, where you say, okay, I want different sets of tasks statically assigned to separate processors, or on the right hand, I have all my tasks and I want them to be run on any available processor, depending on what the operating system thinks. The good thing about the left side, the partitioned way, is that you can still use the analysis that you can do on a monoprocessor system with some additions, but basically what you have is different processors scheduling a set of tasks where you can use rate monotonic analysis for that. While analysis on the right side, when you are doing global scheduling, is not that easy. And as it's in the slide, it's not depending on the tasks that you are writing, depending on your application. None of these schemes is better. In absolute terms, there may be a set of tasks that behave better on a partitioned way, and there may be a set of tasks behaving better on a global scheduling way. So there is not an answer saying, okay, no, if you want to take advantage of your hardware, do this or that. No, it depends also on your application. So, what do we have in the new Ada 2012 language for handling multiprocessors? Because basically what we have in Ada 2005 is there is mention of multiprocessor architecture, saying, okay, if you are in a multiprocessor, you should do this or you should do that. But there is no way to control the underlying architecture. So, what do we have in ADA 2012? First thing we have is the definition of dispatching domains. So, what is a dispatching domain? Basically, a dispatching domain is a set of processors. You take all your processors in your hardware and define disjoint dispatching domains. Say, processor 1, 2, they are one dispatching domain. Processor 3 to 8 is a different dispatching domain. So that's one thing. And from that point, you can allocate tasks to the different dispatching domains. So you define statically the dispatching domains, and you can assign tasks to dispatching domain either statically at the creation time with a pragma. Say I want this, well, and with an aspect if you want. You can assign statically tasks to dispatching domains, and there are runtime calls that allow you to allocate tasks to dispatching domains. So that's what ADA 2012 offers you, so that you can, from the language perspective, you can handle the separation between global allocation and partitioned allocation. You can define, well, I want to allocate in a partitioned way on a per processor or group of processor ways, or doing a global scheduling if you don't define any processor domain, any dispatching domain. So that's what we have in ADA 2012, and it's a bit too complex for safety critical real-time systems, because you can say it's too dynamic, it's difficult to analyze what you have. So what we proposed is a different way. What do we need to address? Basically what we want is what we have in Ravenscar for monoprocessor. It's the advantage, it's reliable, it's very predictable, easy to analyze. As I said, you have all the theory behind rate monotonic analysis. So that's these are the things that we want to keep, and we'd like to keep them when moving to multiprocessors. So the proposal that is in ADA 2012 is based on that. You define all your CPUs in your system. There is a new pragma, which is Pragmatic CPU, which is defined when you specify your task. You say, okay, I want this task, and at the moment when you define priority, for example, say this task has this priority and this task belongs to this processor. And that's what is shown at the bottom at the example. So from the people writing code is as simple as that. Just say, I want this task to run on this processor, and that's it. So how did we do that? How did we implement this model in our runtime and in our compiler? So we based on Ravenscar, of course, and we already had the monoprocessor implementation of Ravenscar, and we wanted to migrate this implementation to multiprocessor. And basically what we had to do is the partitioning mechanism to the runtime, so that we keep a very simple implementation that we can analyze using rate monotonic analysis as you do on a monoprocessor Ravenscar. And one of our goals is, well, we want to base on our current implementation, and of course, we want to be able to add new targets. As I said, This implementation is based on the Xeon 3 processor, which is used in the space domain, but at some point we'll probably have a PowerPC implementation of that, so that we don't want the implementation to be specific to a given processor. I don't know if I need to remind you of Ravenscar, what is the advantage, but the advantage is basically easy to analyze, memory utilization is fixed, you know statically at compilation time the amount of memory that you need, very efficient, the runtime needed to implement and to schedule Ravenscar tasks is really simple, and if you need to go to some kind of certification like DO 178 or the ECSS standard in the space industry, you can do that. And you can still use all the real-time analysis techniques that are very well known. So, what's the underlying model for Ravenscar on multiprocessor? Again, it's very static. Basically, you define only library level protected objects and tasks, and you allocate tasks statically to processors. As simple as that, and they don't move. Once you have allocated a task to a processor, it will be there forever. It is not allowed to move to any other processor. So, the advantage is that you still, on each processor, you have the same scheduling policy that you had on monoprocessor Ravenscar, that you can reuse it very easily. And the analysis can be done on a per CPU way. Basically, you take all the processors, all the tasks allocated to a given processor, and you do the analysis on that subset, and then you do the same thing on the rest of the processors. Obviously, this model allows tasks living in different processors to communicate via protected objects. So that's the thing that you need to add to your analysis. You need to add this interference from one processor, one task running on a given processor, to a task running on a different processor. That's what you need to use to add for your rate monotonic analysis. So, as I said, you do your analysis per processor, and at the implementation level, there is a single runtime for all the system, all the tasks in the system, but there is separate ready queues for each of the processors. And we use some spin lock mechanism to protect shared data between tasks that may run on different processors. Sometimes, for example, if you have a protected object shared among tasks living in different processors, you have a task on processor 1 waiting on a queue of that protected object, and you have a task on processor 3 waking up this previous task. This requires some inter-processor mechanism to trigger an interrupt saying, okay, now there is a new task ready to run on this processor. I am not allowed to touch these ready queues because ready queue can only be modified from the processor to which it belongs. So there is a mechanism to say, okay, there is something to be done in this ready queue. I am not allowed to do that. Please, runtime, please do that. So that's how we handle that. Again, as I said, synchronization is allowed for tasks living in different processors. If you wish, it's obviously less efficient, the implementation is done in such a way that tasks living in a given processor communicating through a protected object are done in an efficient way, because you don't need to handle all the problematic of really parallel access to these protected objects. So that there are mechanisms to simplify the access to these protected objects. And of course, when you need to synchronize entities living in different processors, we use fair locks. I'll explain in 1 or 2 slides what's that about, to avoid problems in synchronizing different processors. So, fair locks. What is a fair lock? Basically, the thing is that typically what you use, it's a kind of spin lock, but the standard implementation of a spin lock doesn't prevent 2 tasks living on 2 different processors to exchange the ownership of this lock all the time. So it may happen that you have 2 tasks on 2 different processors trying to access to a given protected object, and they will exchange the ownership of these protected objects among these 2, and a third one from a different processor can never access to it. The idea of fair locks is very simple. The idea is, I have the ownership of this protected object. I am on processor number 1. Then I finish, and instead of just leaving the ownership and let the other people fight for that, what I'll do is, I'll try to see if there is someone in processor number 2 trying to get the lock. If there is, I'll give it to him. So ownership moves from processor 1 to processor 2, then to processor 3, etc. So there is no risk of a starvation, because it's served in a round-robin fashion, which is in addition easy to analyze. So that's the fair locks is the mechanism that we use to protect both concurrent access to protected objects and concurrent access to the runtime. So how does it work? When you want to have access to a protected object, first thing is you raise your priority to the ceiling locking of the protected object. As we do for a monoprocessor implementation, nothing changes. The advantage of doing that on a multiprocessor system is that if there are different tasks in a given processor trying to get access to that single protected object, in the second step, when you try to get the fair lock, there will only be at most a task from each processor trying to get the fair lock. So, at the first point, on each processor you raise the priority, then you try to get the fair lock. If it's free, you get it and you keep going. If not, you keep looping until it's ready. Then, once you got the lock, you proceed with your protected operation. At the end, as I said, instead of just leaving the ownership of the protected object, you will look at the next processor whether it wants to have access to it or not, and then you transfer ownership if needed, and then you decrease the priority. That's the way it works. And if you are on a monoprocessor environment, you have a single processor, then you remove steps 2 and 4. That's done by the compiler. We'll talk about that later. So in a monoprocessor system, you will not have any kind of overhead because of the multiprocessor implementation. Again, if you have external interrupts, the Ravenscar way is to use a protected interrupt handler. And then there is, we found in our implementation that you need to assign affinities to interrupts. Interrupts must be handled by a concrete processor. Well, it may be handled by any number of processors. In our implementation, what we decided is to assign statically interrupts to given processors. This is not addressed by Ada. There is nothing in the language about how to allocate interrupts to different processors. It's probably something that could be added to the language, because it's interesting to know where the interrupt handler is being handled. Timing services based on the monoprocessor implementation. Access to the clock is very simple. It's a read access, so it doesn't change anything. We keep a single, among the different processors, we keep the same time reference to avoid time drifting. When you need to set a timer because you have a delay, there is potential concurrent access from different processors to this delay queue. So the thing is that we have different delay queues per processor and a common hardware, a common timer for all the processors that is protected by a fair lock. So each processor is allowed to insert or remove tasks from a given queue, and the access to the actual hardware to have the interrupt at the time needed is handled by a fair lock to avoid problems. So, as I said, we based our implementation on the monoprocessor implementation that we had, and in a few words, and the implementation was done by doing that. Basically, where we had a pointer to the ready queue, instead of having a single variable for that, we have an array with the number of processors, so that we have different queues for each processor. The way we handle in the source code, which is shared between monoprocessors and multiprocessor implementation, we have constructions like that. So if we are in a multiprocessor system, we do that, otherwise we don't. And the good thing is that this kind of construction is easily removed by the compiler, because we are using a static constant there. So the compiler on a monoprocessor system will remove anything related to that if. You won't see any reference to that in the object code. So, to finalize, we have done this implementation. It was done, as I said, in the context of an internship at AdaCore in 6 months, with very nice results. We support the model defined in Ada 2012. The code is pretty simple. As I said, well, you need to have these arrays of queues where you have a single queue, but it's not very complex. You need to add this fair locks mechanism, but it's not very complicated neither. And just to make sure that it was like that, we did some performance analysis of the implementation, and we saw that it's basically there is no effect in case of monoprocessor system, because everything is optimized by the compiler. So we don't see any overhead in a monoprocessor implementation, and the overhead that we observed in multiprocessor is not very high. So we are pretty happy with the results. I'm pretty happy with the relative simplicity of the runtime for implementing that. And that's all I wanted to tell.